In the previous module, when we are talking about AR model and showing that how we can find out the coefficients, strictly speaking it is not actually AR model, it is just a linear prediction model. The reason is we were looking at only a deterministic signal, we have not considered it as a random signal. We have just taken that signal is a deterministic one and trying to find out a linear prediction model which fits there. Now, let us take the case that if the signal is a random signal, how we proceed about it. Okay. And to be precise, that AR model is defined only for the assumptions that signal is random, because the driving signal is a white noise which is itself a random process. Okay. So, this difference please keep in mind, and here if we take the yn is a random actually signal. So, error En which is the prediction error of yn is also random. So, in this case the equation 1, that equation 1 what we had for the total square error or a scaled version of it mean square error, it would take a new form. Okay. What we have done, instead of the summation we have used the expectation operator. This is the change. Now, the natural question could be that why we are doing all such tricks. The point is that for the beauty of this parametric model is that when we know that this is the model, we try to find out the model parameters out of the signal. We call for a random process that these values are just ensembles. So, once we have the outputs yn, out of that we find out the model parameters, and once we get the model parameters, we can characterize that process in terms of model parameters. We do not have much need of those exact values of yn which are so important in non-parametric methods. Once we get those model parameter or the model itself, we can say that we can forget about the signal. We know signal is nothing but it is an output at a point of time, it came out of this model. At a different point of time, another set of values may come out of that model, and as we know the model, we can do all the work with the help of that model. So, the signal becomes of less importance after the model is derived, and once we have that all the parameters in our hand. Okay. So, that is the beauty of the parametric model, it gives a compact representation of the whole thing. Now, here let us come back that we have the new definition of the mean square error. Using that, again we go in our known way of finding out the minimum error. So, using that minimum error criteria, that means taking the partial derivative with respect to a case and equating that partial derivative to 0, we get a set of normal equations that is consisting of a case and expectation of that second order terms of y, primarily of the form y n minus k, y n minus I in this form. So, if we solve that, we can get the value of AKs, and again with these expected values we can actually get the mean square error value also with the help of the expected values of y n minus I into y n minus k and AKs. Now, if the signal is a stationary random process, the term that y n minus k, y n minus I, or rather the expectation of this product, we can represent it as the autocorrelation of lag I minus k, and we get actually the same form as previous, that equation number 3, that the equation number 3 which gave us those equations. So, we are getting the same set of normal equations with phi, and here we get a particular characteristics that this matrix is something very interesting. If you look at that, all the diagonal terms, the principal diagonal it is with phi 0, and you will get that off diagonal terms also they are having the same values. Here it is phi 1, it is phi actually minus 1 means again phi 1 for real signal. Okay. So, it has not only the symmetry, all the diagonal terms they are actually having the same values. So, for the real signal, this p by p matrix, it is symmetric and the elements along the diagonals are identical, and such matrix is given a special name as Tweplis matrix. Okay. So, this Tweplis matrix, this is something very special structure, and this equation what we got, it looks very similar to the earlier Wiener filter. That Wiener filter also implemented using a tap delay filter. Here also we have the same structure and same equation. However, there are certain small differences are there. In this case, that the ACF what is used in the left hand side was the ACF of the input in case of the Wiener filter, whereas in this case it is the ACF of the output of the prediction filter. So, this is the first difference, that in the left hand side the coefficients or the terms what we get, though both the case it is ACFs. In case of Wiener filter it was ACF of the input, and in this case the ACF of the prediction filter, that means that of the output signal. The filter vector on the left hand side contains all the filter parameters in both the case. So, what we try to derive the filter parameters in both the case, they are in the left hand side. Next we look at the right hand side, and for the right hand side what we get, that we have the cross correlation between the input and the desired response in case of Wiener filter, whereas for the air model we have again the ACF of the output of the prediction filter. that means that of y. Okay. So, that is the primary difference, though they look similar, because in the left hand side we have autocorrelation and we have all the parameters, they are not exactly the same. Now, to take actually the advantage of the special structure of this matrix, which is a Toeplitz matrix, we can make use of the Levinson-Durbin algorithm. It is an iterative technique which has different benefits. The first benefit is it helps to reduce the complexity. The complexity of the computation or the solution of the set of linear equations. We know that to compute it directly, what we can do, we can take the inverse of that matrix and take it in the right hand side. We can multiply both the sides by the inverse of that autocorrelation matrix. So, left hand side will have those filter parameters, right hand side will have the inverse of the autocorrelation matrix multiplied by the vector of autocorrelation, and then we can get those filter parameters after the multiplication in the right hand side. Now, the amount of computation what we have to do, we can reduce that using the special structure of the Levinson-Darwin algorithm. So, first let us see that how the process is defined for that. Here the steps are given. The first step is that we have to do the initialization, and initialization first the index is 0, and for that the error E 0, it is nothing but the signal autocorrelation at the 0th lag. In other words, when the prediction order is 0, then prediction would be 0. So, the prediction error is nothing but same as that whole signal. So, the energy of that would be same as the signal energy. And now, we have to go through number of iterations, or to be more precise, for p iterations. Okay. So, let us go through those steps. The first point is we need to increment the model order and compute the ith reflection coefficient. Now, if you look at the form of the reflection coefficient, you would get that you have seen this form. This form is nothing but the error of a actually ith order model. Okay. That the ith order model, what would be the prediction error? We are actually using that, and then it is scaled by the previous, the error at the previous model order, that is eta I minus 1. Okay. So, it is a ratio of the two errors we can say. So, this is the reflection coefficient, and after we compute the reflection coefficients, that we have to go for that the next step. For that actually we need to make use of that computation of that a I minus 1 comma j, which suggests that jth model coefficient at the iteration I minus 1. That means, to the previous level, what was the coefficients of the AI prediction coefficients, we make use of that and find out that what is the error, and then we get the the model, that reflection coefficient. Now, we will update actually all the that prediction coefficients, the new one AII, that up to that the previous one it was I value was I minus 1. So, that AI comma I is new, which is appearing first time, that is taken as same as the reflection coefficient, and the other coefficients which were there earlier, they are updated. Those values represented as A I comma j for j is in between 1 to I minus 1. We take what was the previous value in the last iteration into that reflection coefficient into that, we get a reverse, actually a flip kind of thing of the coefficients in the previous iteration, okay, a flip version of it. So, this is the way the updation happens, and we can compute the error vector eta I. It is nothing but the previous error into 1 minus square of the reflection coefficient. So, these steps actually are followed p times, and at the end of it we get the final model parameters AKs. They are given as that at the end of the p iterations, the coefficient values. Okay. So, what we were looking at, how to find out the filter parameters that we get by the that p iterations here. Now, as the model order increase, this total squared error TSE will decrease. Now, let us look at couple of interesting thing that from the book we have taken these points, book of Professor Rangayan. It is written that reflection coefficients may be used to test the stability of the signal, and the next point is, for stability all the reflection coefficients has to be less than unity in magnitude. I have not changed those statements because they are in the book, and if you are following that book you may be a bit ruffled if I change them. But the fact is, if you go through the SMK's book, you will get that reflection coefficients have a nice property that they would always be less than unity in magnitude. Okay? That you can actually convince yourself, you can take an example and compute them, or you can just look at that equations. Let us go back to that, how reflection coefficients are computed. Here if you look at this equation of reflection coefficient, it is nothing but actually the error in the previous, that the present error divided by the previous error. So, as it is, we know we increase the model order, this error decreases, this value cannot be more than 1. It is by design, it would be less than 1. In fact, that is one of the beauty of the Levinson-Durbin algorithm. The filter coefficients it will generate in this way, it will make sure that the filter would be stable, because they would be reflected inside the unit circle. Earlier we have gone through the concept of minimum phase signal, where all the poles and zeros they are reflected inside. Here Levinson-Durbin algorithm, using that reflection coefficient, they are achieving that property. They are reflecting all the poles here, because here we are not dealing with zeros, inside the unit circle, and all those air parameters they are corresponding to the minimum phase signal, or to put it in a more simpler way, that we always get a stable signal. So, these two lines they are not precisely correct, they should be interpreted in a different way, that Levinson-Durbin algorithm that gives stable filter and reflection coefficients make sure that their values or magnitude would be less than unity, and thereby they are actually reflected inside. So, all the coefficients what we get, we could make use of it without any problem of stability. Okay. So, now we can look at how to get the gain factor G. Now, the comparing the air model with the air equation, we need to compare that. So, we take the two equations side by side, both can be written in a way that yn is there in the left hand side. For the air model, right hand side we are getting the values of the output and G times the present input x n. For the error equation, what we are getting in the right hand side, the error term minus actually again the summation of the previous terms multiplied by the corresponding air coefficients. Okay. So, now if we compare these two, what we get, that the error term is nothing but G times the present input signal. So, what we can do, that we can get that input signal is proportional to the error signal, or we can say other way round, the error signal is proportional to the input irrespective of the nature of input. So, when we look at the output energy, and that is for a fixed Hz, that means Hz is computed, we need to have a energy balance in both the sides, in the input and the output, because of the preservation of the energy. So, looking at that, what we can get, that G square is equal to that the prediction error for phi y equal to 0. That means, what we are suggesting, that the input, if it is of say unit energy, then the sole energy of the driving is because of the scaling factor G. So, that is same as the output error, and we already know the expression of the output error. So, we can get G unique up to scaling. The scaling factor is the scaling of the input signal. So, the simplest thing we can do, we can assume that driving signal energy is 1, and for that what is the value of the G we can get from the energy of that error of prediction. So, with that we complete one part. Next we look at a different technique, of computing the actually the error coefficients. This new technique is called covariance method. The previous technique, as we are using the autocorrelation, we can call them as the autocorrelation method for computing the error coefficients. So, in this covariance method, again we use the same equation 1 and 2. The only change occurs in the range of minimization. The previous technique, we have taken the range is minus infinity to plus infinity, and however, that got limited because of the limited number of sample, but here we start with the fact that we have signals from index 0 to capital N minus 1. Okay? And over these, that if we minimize that error, we get a little different form. In this case, we get the equations in this way using that autocorrelation, this coefficients a k's, and we get a new term called c k minus k comma 1 or k comma I in this form. So, and these C's are capital C's are the autocorrelation function, we will get that, but before that we look at the form of total squared error. Again it is expressed in terms of the covariance function C, which is replacing the autocorrelation function used in the previous autocorrelation method, and the form of that C I comma k is very similar to the previous one. However, there is some differences that we observe. That matrix formed by the covariance function, it is again what we are getting, it is symmetric, because C I comma k and C k comma I, it is same, because the terms, the product is a commutative operation. So, the values are same if we change the order. So, again we get a symmetric matrix, but everything is not same. The element along the diagonal are not same. That C 00, C 11, C 22, they are not same. Okay. There is a change, and here we are showing that change in a quantitative way. If I look at C I comma I plus 1 comma k plus 1 in a more general sense, it is using that C I comma k plus we are having a new term, and we need to eliminate one term out of C I comma k. So, there is a change, or we can say that the summation window is shifted by one place. Okay. So, that creates the difference, we do not get anymore the Toeplitz matrix. So, what we get instead, the computation of the covariance coefficients, for that we need the data y n, we need it from minus p to n minus 1 for that range. So, we have to, if the data is given from 0 to or 1 to n, we need to re-index it and index it in this way, so that we have all the values available the output signal is available from the lag or from the instance minus p to capital N minus 1. Okay. However, that difference that is created between the autocorrelation and autocovariance method, this distinction disappears at the interval of summation tends to infinity. If we have more and more data, that difference actually disappears, which is caused by addition and the deletion of one sample from two different sites. Okay. So, they actually go to the same thing. So, that is about the autocovariance method, and we stop here for this session. Thank you.